So as we continue the review, question 11 asks us to find the variables that maximize. Okay, so I want to maximize. So I have to maximize the product of x, y. So right away, I know my objective function is to maximize the product. So I'm going to say product equals x, y. Now, I notice I have it in two variables, so I'm going to keep reading. So then it says, given x plus 5y equals 22. So here is the given, so that is my constraint. All right, and then they want me to identify, besides finding the variables, I have to identify the final product. So I'm actually going to have three answers, x, y, and then the product, which I'm calling p. Okay, so we have to rewrite our objective function so that I only have one variable. So why don't I say, it looks to me like maybe the easiest thing is to say that x equals 22 minus 5y. So I'm going to replace my x. So my objective function, new and improved, is going to be p equals, and I have my x first, but I'm going to replace that with, and using parentheses, 22 minus 5y. Okay, that times my y. So my y is just plain old y, like it's always been. Let me just fix this again. Okay, this is y. All right, my first step is going to be to distribute this. So let me just distribute. My pen is misbehaving here. Okay, so p equals 22y minus 5y squared. Okay, so that's good. So let's get p prime. P prime equals 22 minus 10y. Okay, as long as I'm working, I might as well go ahead and take the second derivative. My second derivative will always be negative 10. If my second derivative is always negative, that means that I found a max, and look, that's what I needed to find, so I'm good. Alright, so let me work on setting my first derivative equal to 0 so I can get my critical values. So it looks like 22 equals 10y, divide by 10, divide by 10. I'm getting y equals 2.2. Alright, hopefully you are getting that as well. So if y is 2.2, how do I get my x? Well, I see from above, so far I'm going to box this. I know y is 2.2. X has to equal 22 minus 5y. If I plug in a 2.2 for my y, then I get an x value, so just doing the math here, that's 22 minus 11, so my x is equal to 11. So that's my x value. So I have an x and a y, so all that's left is the product. So the product is just going to be the x times the y, so 11 times my 2.2, and if you do that math, you will get a product of 24.2. I have no units, so once I have these three answers, I am good to go. Alright, so that should make sense to you. Make sure you understand how to work with the constraints and the optimization functions. Okay, here we have another optimization problem. This time we're going to maximize the size of a garden. Now notice it says I'm planting my garden against a wall and I have 100 feet of fencing. So I have 100 feet of fencing. That is going to be my constraint, and let's see what we're going to do. So I'm going to make this my y, this my y, and this my x. Now why aren't I filling in the opposite x? I'm not filling it in because right here this is a wall, so the wall does not require any fencing. Okay, so now it says, what is the length of the sides of my rectangular garden that will maximize my garden area? So we want to maximize area. So area equals x times y. All right, so that's going to be my objective function. So area equals x times y. My constraint is that I have 100 feet of fencing, so that's a perimeter. So 100 is going to equal y plus x. So that makes it x plus 2y, not plus y squared. So make sure you don't make a mistake with that. It's easy to do. All right, so let's get my equation for area, because I'm going to maximize that. Area equals xy when I have two variables. I don't want two variables. So area equals, let's substitute x equals 100 minus 2y for my x. Okay, so x equals 100 minus 2y. So here comes the x substitution. 100 minus 2y times my y. So go ahead and distribute that, or if you want to use the product rule to take a derivative, you certainly may. Now I'm ready to take my derivative. So I didn't want, what did I just do? This is squared. Okay, so my derivative is going to be 100 minus 4y. Okay, I'm going to go ahead and take my second derivative. That's a minus 4. Since it's minus, I know my function will be maximized at the critical values that I find. Okay, what are your critical values? So if 100 equals 4y, y has to be 25. And in this case, we are dealing with feet. So y is 25 feet. Okay, so if y is 25 feet, then how do I figure out my x? Well, I see right here that x equals 100 minus 2y. So x will equal 100 minus 2 times 25, which is 50. So that's going to make x equal to 50 feet. Okay, so my dimensions are going to be 50 feet by 25 feet, and that's what they wanted. Now, notice they could have also asked you for the amount of area you have in your garden. In that case, you would just find that product. But these are your final answers. These are my measurements. Now, depending on how you labeled your picture, you may have different values for x and y, but the dimensions will still be 25 by 50 feet, no matter how you do it. So don't worry about if you've called your x my y or your y my x. It's totally fine as long as you have shown the correct word. Okay, here's another optimization problem, and in this case we are talking about a cylinder. So it says a cylinder is made to hold a volume of 1,000 cubic centimeters of crude oil. So probably the first thing I would do is do a little sketch of what the cylinder looks like. Okay, so it's telling me that the volume is 1,000 cubic centimeters. Okay, so I've gone ahead and done some setting up here. So I have a sketch of the crude oil container, and I've indicated the radius and the height. I then down below started working on surface area, so we'll get to that in a second. Okay, so they're telling me that the cylinder is made to hold a volume of 1,000 cubic centimeters of crude oil. Find the dimensions that will minimize the metal surface area of the cylinder. And they said assume the cylinder has a top and a bottom. Verify that you have minimized the surface area by analyzing the second derivative. And I'm saying too, I'm reminding you this is similar to the soup can problem that we did when I gave you the 2.5 challenging problems to work on. I believe it was the last problem in that set. So my constraint is that my volume is going to be 1,000 cubic centimeters. So what is volume? Volume is the area of the base, which is pi r squared, times the height. Okay, so now I'm going to work on the constraint. So 1,000 equals pi r squared times the height. Okay, that's my constraint. So it's not my objective. Okay, I already know that the volume has to be that. Let's talk about surface area now. So surface area, in that soup problem, I sketched out how to find surface area. If you cut that crude oil container open and lie the center part out flat, it looks like this, all right? So that area is just 2 pi r, which was the circumference, times the height. So that's part of the surface area. So I have 2 pi r h, 2 pi r h, plus this has a top and the bottom. So the area of the top is pi r squared, and so is the area of the bottom. So I have 2 of those, 2 pi r squared. All right, so notice I have 2 variables in my objective function, which is frequently the case. The easiest thing is to substitute out for the h, and looking at my constraint, I can see that 1,000 divided by pi r squared will equal my h. So that's my next step, rewriting my objective function without the extra variable. So 2 pi r, h is going to be 1,000 divided by pi r squared, and then plus 2 pi r squared. Okay, let's clean it up a little bit more. Surface area equals, so 2 times 1,000 is 2,000. So I have 2,000. Then I have the pi's will cancel, and the r will be the power r to the negative 1. So make sure you can see what I've just done. Plus the 2 pi r squared that we had previously. So it's an optimization. I'm going to take the first derivative, and that gets me negative 2,000 r to the negative 2 plus 4 pi r. Since I know I have to do a second derivative test, I might as well go ahead and take the second derivative. So negative 2 times a negative 2,000 is a positive 4,000 r to the negative 3 plus 4 pi. Okay, so just before I do my actual test, I see that as long as r is positive, this will be positive. If it's positive, it's going to indeed minimize it. So when I do my second derivative test, I will talk about that. So we now need to go back and work some more with our first derivative. So let's do that on the next page, because I need to get my critical value. Okay, so we have our first derivative, but remember I said that those negative exponents are great for taking derivatives, but not very helpful in evaluating. So I'm going to write this with my power being positive in the denominator. Okay, so that has to equal 0. So the result is that 2,000 r squared equals 4 pi r. So doing a little multiplication, I get 4 pi r squared equals 2,000. Okay, so let me correct that for just a sec. So r squared times 4 pi r is 4 pi r cubed. So let me write a cubed here. Okay, so r cubed is going to be 2,000 divided by 4 pi. So can I do something with that? I probably could, but let's just say, for the record, that r is going to be 2,000 over 4 pi to the 1/3 power. All right, because I took the cubic root. All right, so I have that value. Now let's go back and see if we can see what h was, because so far I have a value for r, which is the radius. So I'm going to go back and let's see how h related to it. Okay, so I see that h was 1,000 over pi r squared. So if h equals 1,000 over pi r squared, if you square r, look what happens. I have the 2,000 4 pi to the 1/3. If I square that, I get 2,000 4 pi to the 2/3. Okay? Because you add your exponents. So there you have it. I now have h and I have r. So I have my variables, but the next thing they want us to do is to verify that you've minimized surface area by analyzing the second derivative. Okay, so let's go back and we're going to grab our second derivative. Oop, went back too far. Okay, so let's grab all of this. So let me see if I can get this to copy. Oop, there we go. Okay, so I really need this. Okay, copy. And we'll put it on this page. And now we'll talk about it. Okay, so what did I say about this? I said that if I was going to do a second derivative test, so I would put my r value, and let's go back and we'll grab that r value. Okay, so there's my r value. So that r value is itself a positive number. If it is positive, then my second derivative test will tell me that the result is to have a function that's concave up. So my statement would be, at the CV of, and I would quote that, f prime prime of that critical value is going to be greater than 0, and therefore the function is concave up, which yields a minimum. And we wanted to minimize the surface area, so we're all set.